Hi. So this week we're gonna study graphs, and this lecture it's about primarily the fundamentals of graph data structures, and we're gonna look at a few algorithms for dealing with some of the common problems. And so just to start with an overview, we're going to look at some terminology of a graph theory, and then we're going to look at how to actually represent graphs in computer memory, and which we actually talk about in our overview of data structures lecture. And we will look at how to design a graph as an ADT, and then we'll explore a few of the traversal algorithms like tree traversal. We have a graph traversal, and then we also look at two very sort of a fundamental classical operations on graphs, shortest path and a minimal spanning tree. Now, to start with, we need to look at, okay, why do we use graphs, right? So there is actually an old classical problem, and in the city of Königsberg, which is in now modern day Russia, and this is a really old one actually in the I believe is the 19th century. And so the geography of that little town is that there are this blue color here. You see, this is the river, a river Prego, and it flows through around an island here. And then there is also another small island over there. And so these double lines here are actually bridges. And so the question is, can we uh, basically, let's say we drive through all the bridges, can we actually, traverse all the bridges and then come back to where you started from exactly once? That was sort of the challenge here. And that question was answered by Euler, obviously a famous mathematician you should be aware of. And so Euler answered this question by uh, abstract out the problem into a graph structures. And as you see here, like this island marked as A and D, and then we have a pieces of the land marked as, C and a B, right? So it's, translating into those are the vertices and in a graph data structure. And then the bridges are marked as edges between those, vertices. And so this is a graph representation of that problem. And so Euler was able to answer that question by doing this way. So this was sort of the beginning that commonly recognized as the beginning of the graph theory. And we have actually seen the graph theory being applied to many different problems. And in the real world, indeed, the graphs are actually everywhere. And we may use graphs to model electrical circuits in the chip design and chemical compounds, chemical engineering, and highway maps like our, Google Maps or navigation systems. And thinking of these roads, you have, let's say in a town, you have traffic lights, and those lights would perhaps can be represented as the intersections would be as a vertices, and then you have edges of which are the roads, and then you figure out how to navigate from one point to another. And so there are obviously optimization problems when you have a graph problem, a graph representation, and you may want to find the shortest route, let's say for mail delivery, right? Logistics, linguistics, um, and genetics and social science, and etc. There are many different places where this is used. Federico, I've already started. Okay. You're here? Can you hear me?
Yes, Professor.
Okay, so I just started with the introduction. You didn't miss much. You can go back. Okay, I'm gonna move on. I did not know if you're gonna come on or not. All right.
Yes, I'm sorry.
So yeah, my internet is today is a bit slow. I'm not sharing my video. All right.
Yes, it's working. It's okay.
Okay. Okay. All right. Okay. So it was just an introduction, introducing the graph theory on a classical problem. Anyway, you can go back afterwards. So let's look at a couple of definitions and notations when we talk about graphs. And so far, we have studied trees. We know, nodes and the edges, and that particular data structure where you notice the tree is, in fact, a tree is a graph. Um, it's just, so happens that that is a graph you can identify sort of a root node. So they are somewhat related. So specifically for graph, we have to represent the graph in a different manner. So let's kind of mathematically, a graph is, okay, so let's look at a couple of things. So we say A exists in a set of X, right? X is a set. So it means just A is an element of the set X. This is a mathematical notation here. We may also have a subset relationship. A set Y is a subset of a set of X. So essentially every element of a Y is also an element of X. And then set relationships also have intersection and a union. I believe most of you should be already familiar with those concepts, so I'm not gonna go through each one. And we may also have operation, Cartesian product, right? A product B. So this is essentially all the ordered pairs of elements of A and B, essentially pairs of A, B elements. A is, is in from A, set A, B is from set B. So this is just a little bit of review, and we're not necessarily going to get into the math aspects, but just something to be aware of. When it comes to, designing algorithms, and some of those things are going to apply, but we're not going to get into too deep into those yet. Okay, so for a graph G, so the G, just, the mathematical can be notated as a, as two elements. You have V and then you have E. Now V is actually a finite non-empty set of vertices of G. So vertices, like in analogy with the trees, would be those nodes, all right? So those nodes in graph are called the vertices, or vertex, vertices, the plural. And then we have edges. E is the edges, and edges, this is obviously a subset of V Cartesian product V. Essentially is, these are the edges among the vertices. If you have all the vertices connected, and then it would be equal to that. But then if otherwise, normally you don't have all the, vertices connected. So it's a subset typically, the edges are. And then elements in E are pairs of elements of a V, right? So this is kind of what we're talking about. So when we look at a picture, we're gonna, it makes more sense. E is called a set of edges. So we're gonna actually, let's just take a look at a graph notation. I mean, this is, hopefully this is not an alien to you guys, and you probably have seen it somewhere. So if you look at this graph, I mean, obviously you cannot identify a particular, it's not a tree, right? Obviously it's not a tree. You cannot take one node out as like a root and the other things. In a tree, as an example, you don't have cycles. Here we have seen cycles as an example, right? So let's look at a couple more definitions. Directed graph. Now, directed graph, or sometimes called digraph, this means the elements of E means edges, right? The edges are ordered pairs. That means these edges have a direction. For example, in this case, when we look at this graph, it doesn't have a direction. This is actually it's not directed essentially. This is the not directed, and if it's directed with it, you would see an arrow representation. So that would be an undirected graph. What we're seeing that particular example. So here take a look at a couple more things. So this notation, parentheses u comma v, this represents an edge in a directed graph, and the origin is u, destination is v. It's an edge from u to v. So it's pretty straightforward. And then a subgraph h of g. Now this seems a little complicated, but it really just means you have, only a subset of vertices from G, and also a subset of edges from G, and that comprise a subgraph. Okay, so we're gonna look at one of the algorithms later on, just in a bit, and that will be essentially what we're looking for is a subgraph. And so a subgraph here, I don't think this example here particularly shows a subgraph. For example, right, if this is a graph, I just take this portion of it, 1, 2, 4, with the edges, right? These vertices with the edges, there would be a subgraph of this graph. Right? It's straightforward to understand. The notations are a little scary, but this is very simple. So these are directed graphs, right? So you see typically the edges are represented as arrows. Now, of course, you can also have cycles. You may, from 0 to 1, you have one arrow. Maybe you have one back to 0 too. I mean, that happens. So it's all possibility. So this just shows an example where you see there's cycles here like this. And okay, so a couple more things. Adjacent, in terms of relationship, when we say, if there's an edge from one vertex to another, this edge, UV edge, and that means these two vertices are adjacent to each other. That just means adjacent. Adjacent means essentially they are connected. That's what adjacent means. They're connected. And then incident. I don't think this concept matters much. We don't really use much of this concept, so I'm gonna skip this one. And parallel edges, it means that you may have the same pair of vertices that are associated. This, we don't have an example right here. It really, in our algorithms that we're discussing today, we're not gonna actually look at a parallel. It may not really matter too much. Let's say from 8 to 5, you have an edge. You may have another edge, but then perhaps you have them labeled somehow. So those are sort of variations of graphs we're not going to study just yet. And we're going to look at sort of simple classical ones. Now, simple graphs means in this particular context means when there's no loops or parallel edges, loops or cycles. And so, well, no, not cycles, loop. Okay, loop is kind of a pertinent. So the concept of loop, imagine from this node 2, I have a loop, an arrow goes back to itself. That can happen if we study, computational. Let's say there is a particular branch of a computer science theory, like automata theory, and then where you may study regular expressions. And now, sure, you've heard about regular expressions, where the graphs represented there, you will see a lot of those loops, like, that is totally possible there. So, but that's not what we're studying here, but that's kind of loop. So the graphs we're studying here, there's gonna be no loops, and then there's no parallel edges, like you have sort of two edges from one node to one vertex to another. So that's what we call simple graphs. That's what we're studying here. Okay. A path. What's a path in a graph? We know what is a path in a tree, right? Now it's similar. A path in a graph is a sequence of vertices, and they are connected from one to another. Now, this is just a little more formal definition. If we just look at an example here, like from 0 to 1 to 2 to 7, that's a path, right? That would be a path from 0 all the way to 7 via 1 and 2. And so that's really what path is. Connected to vertices, there's a path from a U to a V. And so, like the example from 0 to 7, these are connected through a path. So they are connected. Now, simple path, what's a simple path? Simple path means it's a path in which all the vertices are distinct. Well, with an exception. The first and the last could be the same. So essentially allows you to have a cycle in a sense. So a simple path means that all the vertices are distinct. And so the example that I just gave you, 0, 1, 2, 7, that's a simple path. And let's see if I can run a loop. Not a loop, but a cycle. From 3, 4, 5, okay, 3 or 4, okay, 0, actually. Let's see, so I'm looking for a cycle here. So here's a cycle. 0 to 3, to 4, to 8, to 6, back to 0, right? So that would be, we have identified a cycle, essentially. This is also a path. This is a, in the definition you will have here, that's called a simple path. So that's what the kind of path that we study here. And cycle, so that's actually a cycle that we just notified, we just recognized from that particular example. We have a simple path in which the first and last vertices are the same. So that was just an example that we identified. That's a cycle. And a connected, so essentially what's a connected graph? A connected graph means the path exists from any vertex to another vertex. And that's a connected graph. This is what it means. The graph is connected. So you don't have, for example, you don't have, let's say this is your graph. Maybe if I don't have any edges that go to like node 3, that 3 is just on its own. That is still a graph, but this graph is not connected, right? So connected means all the vertices are connected together via some edges, right? That's really just what that means. A component, just be aware of the concept, and it's not necessarily super important in terms of our algorithms and our discussion in this course, but what is a component? A component of a graph. A component of a graph is the maximum subset of connected vertices. And, you know, it is basically, let's say, imagine, right? I said, if we did not have edges, these two edges are deleted, let's say, 3 is standalone, but this together is still a graph. Okay, so that by definition, that's still a graph, even though you don't have edges connecting 3, the vertex 3, that's fine. But in this particular case, this portion 1, 2, 4, 5, this part would be the component of the graph. Essentially, is the maximum, you know, kind of the largest subgraph, if you will, okay, informally. That's really what that is. That's a component. So in a connected graph G, if there is an edge from U to V, then U is adjacent to V and V is adjacent from U. So that's the adjacency that we talk about, that concept of adjacent, and that's really nothing new here. And what's a strongly connected graph? A strongly connected graph is a graph in which any two vertices in G are connected. Any vertices are connected. So that would be a strongly, so we don't have an example here. Let's say any two, basically any two are connected. Let's say I have an edge from 1 to 5. Well, let's see. You know what? 1 to 5, not necessarily directly. When connected means you have to have a path to it. So this would be a strongly connected. So this is actually an example of strongly connected graph, because any two, right? And let's see. No, not necessarily. So there's one thing that's missing. 3 to 5, I don't see a path from 3 to 5. So let's say if we add a 3 to 5, some edge here, so that there's a path from 3 to 5, then they would be strongly connected. So this is not a strongly connected graph. So strongly connected graph basically means that any two vertices are connected via some path. It does not, the path could be just one or multiple edges, right? So they have to be connected. All right, so that's just a couple of concepts about graph that sort of just to understand what that sort of mathematical, this is actually, graph is a mathematical concept, and we are more interested in studying this as a data structure, how to actually have a computer, calculate and solve problems with graphs, right? So we want to write a programs that process, manipulate graphs. So we need to represent a graph in memory. So there are two primary ways of representing a graph. And we have actually sort of discussed this in our overview lecture of data structures. And so let's kind of review this again, right? Adjacency matrix is one way to represent. Now, we know what adjacency means, right? Adjacency, basically for any vertices, if there's an edge in between, they're adjacent. So if there is an edge, for every edge, essentially for every edge that's in the graph, we're gonna mark that elements. Think of a two-dimensional array as a matrix. Two-dimensional matrix, right? Or representing as an array in memory. And you would essentially mark that edge as a true or false, a true value, right? Or one or true, right? A Boolean value, perhaps. And it may not be a Boolean value. If you're doing some certain calculation, you may just use the value one. It depends on your usage. But anyway, the idea is if there's an edge between these two vertices, thinking of, just draw a table. If you just imagine a table, on the left hand side, you have all the vertices marked 0, 1, 2, 3, 4. And on the top row, think of Excel, right? On the top, you have those cells, the same thing. So it's a two-dimensional, and then you mark those places where there's actually an edge, you mark that as 1. If there's no edge, it's a 0. So obviously, if you have an undirected graph, we'll see that it's a symmetric, right? The matrix is going to be symmetric because from vertex 1 to 3 is the same if it's from 3 back to 1, right? Thinking of that table. So in that case, really, half of that is going to be mirrored the same as the other. So in a sense, it's sort of an inefficient way of representing the graph, if you think about it, if your graph is kind of large. Now, another way to represent adjacency is adjacency list. So adjacency list is that we're gonna basically, for every vertex, we're gonna maintain a linked list, essentially. Let's say you have 10 vertices, and then you would have essentially 10 linked lists, and then you have those 10 linked lists stored in an array. So you can access each one of them. Now, what is the linked list about? The linked list is essentially about all the nodes, essentially all the vertices that are represented as an edge in. So if for a particular, let's say you have a vertex, let's say you mark as number 3, right? It's ID number 3, and this linked list contains the linked list for that particular vertex contains all the edges that are essentially, if it's directed, it would be pointing to it as a destination. If it's undirected, then it doesn't really matter, right? So it contains the edges that are adjacent to this particular vertex. So that's how we represent it, okay? And so here's an example here. If you look at this adjacency list, right? So let's say we have a graph. This is actually from the prior example. We see a picture there. But anyways, you have 1, 2, 3, 4, 5 vertices. And for each of them, you have the adjacent vertices represented here. This says figure 24. Actually, let's take a look at figure 24. Look at one thing, 24. Okay, so for vertex 1, you have actually a 2 and a 4 that are adjacent, right? So you see 2 and a 4, there's an adjacent to it. So that's kind of how you represent, and then the other things are the same thing. Now 3, there's nothing, right? So the vertex 3, as you look at 3, There's no other edge that goes from 3. So that's really what that is. It's just, this is an example, and this is just similarly just a larger graph, adjacency list. So, and in the algorithms that we're going to be discussing, and actually in our sample code from the textbook, this is sort of the representation we use. So what are the operations on a graph? Well, obviously you have to be able to create the graph, and then you may want to somehow clear the graph. I don't know if that is super important, but this might be, you know, relevant if you're manipulating the graph in some fashion, right? But the algorithms we're going to study actually don't really necessarily manipulate. But if you do, then you might want, you know. So anyway, this is one of the potential operations. We may want to determine if the graph is empty or not. We may want to traverse the graph. So see, you know, obviously you want to traverse a graph. Perhaps you're looking for something in the graph. Perhaps you're looking for a path. You see, maybe we're trying to find a path that's either the shortest or the longest. So that kind of a maximal or minimal property is something we're usually interested in. Like if you have a, remember that, you know, a heap, well, not heap, just say a tree data structure. Well, heap is you know, a way to represent that we want to have the sort of maximum value or the minimum value at the very top as the root. But that's one of the things that we're usually interested in. And then we may want to just, you know, somehow print it out or visit the graph and do something about it. So those are the possible operations, and there are actually sample code that's about those things. And so let's assume we're going to use the adjacency list representation. And so for each vertex V, in the vertices adjacent to V are stored in the linked list associated with a V in a directed graph. The vertices adjacent to V are called immediate successors. So it's just another term that we might call them. And then to manage the data, let's say we're going to use what we have before, unordered linked list. And so you'll see that example in our sample code in Goodiebag. So if we're going to design an ADT for graph, and at a very minimum, right, basic thing, we say we're going to have a couple of sample operations. And now, not necessarily this is the optimal thing, but just for our discussion purposes, this one have a couple of operations for a graph ADT, right? We want to determine, have the size and be able to traverse. So traversing a graph, you know, obviously is important, right? You want to be able to visit the node, the vertices, and then be able to, you know, find out the value or do something about it. And so traversing a graph is similar to traversing a binary tree, as I noted before. But then, however, a graph might have cycles, so there are going to be differences. It's not just about, oh, left child, right child, that kind of thing. And so you have to be strategic. You have to actually kind of remember what vertices you have visited before, so you don't go in circles, right? And sometimes you may not be able to traverse the entire graph from a single vertex because your graph may not be strongly connected. You may not be able to get to all the other vertices from a particular place. I mean, that's entirely possible. And so there are two primary traversal algorithms. Now you can draw an analogy with the trees. Trees, you have you know, pre-order, in-order, and post-order traversal. Remember. Now, but with the graph, essentially we just have a two traversal, depth first and breadth first. Now, depth first, that is actually very similar to what in a tree scenario. The tree scenario, it would be, let's see, that would be a pre-order. That would be a pre-order traversal. That would be depth first, right? And again, we're going to look at the example, see how this actually works. And breadth first is probably the in order situation. Anyway, so I'm trying to draw an analogy with what you already know. So depth first traversal at a given node, instead of reading this, I think let's actually look at the example. So suppose we have a graph here, and the let's say we're gonna start from 0. Let's say our 0 is our source vertex. We're gonna start from this. Now you could potentially start from anywhere. That's whatever you define. You want your problems, to start with. So let's just say we start from 0, and then so the depth first would be like this, right? Just kind of go this hand by hand. Now we're gonna look at there are 2 vertices connected from 0. You have a 1, right? And you have 3, right? So, and then what you do is obviously, if you're doing the breadth first, you see actually there's 2 examples, but let's look at depth first. Depth first. So depth first means we're gonna visit that node. That's it's right from 0. You have a adjacent node that's called a 1, a vertex, and then you go from 1 to and then just continue. And then from 1 to 4, right? And then you continue, and then you look, okay, it looks like a 4, we hit the end of it. So then we're gonna print out 4. So we visit a 4. But then we need to go back. There's another vertex from 0 we have not visited. So we're gonna visit 3. Now from 3, we're gonna continue, see how far we can go. And then we see 2, right? We'll print out 2. And then we get 5. Then we have a 7 and it's 8. Now with the 7 and 8, so let's say we pick one, let's say the smaller value first. So we'll start with the 7. And then from the 7, there's no more outgoing edges, right? So that stops here. And then we're going to continue with the 8. So we'll look at the 8. Then there's nothing outgoing. So we're done with 8. So now from this point on, we have visited all the branches starting from 0, right? Now we have other things that we have not visited. So we have what's remaining. They cannot be reached from 0 essentially. So we have to just deal with the 6 that's remaining, and then we have to deal with the 9. So that's really, remember we have the vertices remembered, right? It depends on your representation. So you're gonna have to basically visit all the nodes, all the vertices, sorry. And the breadth first would be a little different. And the breadth first would be from 0, and then you're gonna visit a 1 and a 3. Okay, and then basically we want to deal with the adjacent vertices first. So we have 0, 1, 3, and then from the adjacent vertices like 1 and 3, we're gonna, let's say we pick the lower number first, and from 1 we have another one. It's called 4. So essentially, thinking about from the tree traversal, we're going layer by layer from the roots, and it go one layer down and it go another layer down, like in that sense, if you will. Okay, so we have 4. We visited 4, but then we need to go back, look at the previous layer 3, right? In terms of the length of the path. So we'll check a 3 now. 3 was visited, and now we're going to check what's coming from 3. 3 connected to 2, so we're going to have 2. So we'll print out 2 in this case. We'll visit 2. Now, we're going to look at another layer, right? So from 4, there's nothing outgoing, so that's done. But then there's something outgoing from 2, so we're gonna visit a 5. So 5 is visited now, and then go one more layer deep, sort of one more leg essentially on that path. So now we have 7 and 8. Okay, so 7 and 8, they're at the end of it. Thinking of it like almost like the leaf nodes of the tree. I mean, this is not a tree. I try to draw an analogy, but graph is sort of a little more complicated shapes. And then you have a 6 and 9 that are left over. They are not connected from our 0. It cannot be reached. So then you start from the 6. Of course, those vertices that are visited already, you don't really start from 6 and go into 4 to 7 because they have been visited already. So see, as we traverse, we need to remember what vertices have been visited. So every vertex will be visited once. So that's a breadth first idea, and we'll take a look at the Well, actually, I'll leave that to you to look at the code from the textbook. It's also put in the goodie bag you can play with. So the implementation, this is actually mentioning here, for breadth first traversal, remember we have to kind of know to go back to previous layer, right? So an idea is to use a queue to sort of remember how to do that. So now the actually the depth first traversal, in that case, a stack data structure would be suitable. That's the actual implementation of these algorithms. But let's take a look at, now we have traversal. Traversal is sort of a fundamental operation on a graph that you may visit a graph and you know, do certain things. You know, visit them and then just print out the values, for example. Depends on what you're trying to do. But then that gives you a taste of how to traverse a graph. And now let's try to solve some interesting problems. Shortest path. Now, why shortest path is important? Suppose you're doing a navigation, you're designing. So here's your abstract graph of, you know, intersections and rows and stuff. That's, you know, or points of interest on a map. You want to route a navigation plan, right? From a source vertex to a destination vertex, and they want to find out the shortest path, right? Suppose that's what we're interested in. Now, of course, the shortest path, we can define this as perhaps distance, the shortest distance in miles, or maybe the shortest time, right? So you could potentially define what is a shortest, you have different meaning. So in an abstract manner, how we can deal with this in algorithmically, so as in an algorithm, you just want to have a weight on the edges. So essentially every edge will put a weight on them. So far we have seen examples, there's nothing on the edges, right? So the way to do this is we're gonna put a weight on the edges. So an edge would be weighted, and a weight is basically a non-negative, a real number. It could be 0, could be a positive number, essentially. And so we have a value. That value is application specific. And a weighted graph basically means that every edge has a non-negative weight, all right? And so the weight, now we also gonna study, when we talk about the algorithms for shortest path, we actually have to also kind of define, there's a weight for the path. The weight of the path is very straightforward. It basically means it's the sum of all the weights of the edges on the path. We know what a path is. From a source vertex to a destination vertex, you know, you have a path to it. And all the edges, you just combine all the weights, so you get the weight of the path. So the shortest path means you find a path that has the smallest weight. That's really what the problem is. So there is a well-known algorithm. Now, obviously, this is not the only algorithm. There's a pretty good, decent algorithm that's developed by Dijkstra, right? So Dijkstra, if you study math, you probably have heard this name a couple of times in different places. But Dijkstra, it's a very instrumental, I would say, you know, very important figure in computer science. And he actually, you know, passed away not very long ago, maybe about 10, 15 years ago. And he has contributed to computer science so many areas, like operating system, concurrent programming, programming languages, obviously graph theory here we're studying. This is an algorithm named after him as, you know, Dijkstra's algorithm. And he has, you know, a vast areas of research that, you know, essentially without his contribution, computer science wouldn't be here like what we have today. I mean, it's a very important figure. You can read out more about this person, and he's Dutch. It's a very interesting story behind it. Anyway, so this is a algorithm. It's a simple algorithm, but you know, a lot of the algorithms you can be simple once somebody else has developed it. But this is to find the shortest path. Now, how does it work? And then, so this is perhaps it's a little dry here, but we're going to look at a concrete example. So suppose you have a graph G, and the G has n vertices, and then we have a the vertices represented in the array v1 to vn, and then we have a W that's a two-dimensional array that represents the weights. So the weights from, suppose we have an edge in the graph. Now you visualize that graph example we had before. If you have an edge, and then the element, the cell in that two-dimensional matrix would be the actual weight of that edge. Now, if there's no edge in between these two vertices represented by the two indexes, then we just put an infinity in there. Now, infinity in a computer sense, when you write a program, just means it's the maximum value represented by that particular data type. Right? If you're using an integer, just use the maximum integer to represent infinity. So the algorithm goes like this, and it might be a little hard to understand with this. So I'm not gonna really read through this actually. I'm just gonna, let's look at the example, okay? And there's a sample code. The actual implementation is in the Gutenberg, and we're gonna probably look at this thing a little bit. And there's annotations in there, we'll see. So let's look at this weighted graph. Right? Let's say we have this as an example. This is our current graph. That's we create this graph, we represent this in memory. We have you know, sort of 5 vertices, and then the edges are weighted. Okay. It's a directed graph, obviously. You see those arrows. Now, so the first thing we do is we initialize a array called the smallest weight. And this array, so remember the index. Now this is for simplification. I mean, an index of this array, 0, 1, 2, 3, 4, they correspond to the vertex number you see in the graph. Okay, so 0 is the 0th index right here. So we'll put down the values to start with. We initialize. This is we're initializing first. We initialize this for the, suppose the 0 vertex, 0, is our source vertex. We're starting from the source, we want to find the shortest path, okay, within the graph. So this is basically, we're starting from 0. Now from 0, we actually just put a 0 in here, the smallest weight. You know, we say 0 to 0 is 0. Imagine we draw a path from 0 to 0 by itself, right? So it's a 0. Okay, there's no weight. Now, for 1 means this is means we'll go from 0, which is the source of vertex, to 1. It has a weight of 16. That's marked on the edges. Okay, so we start with this. This is initialization. We haven't gone through more. We're going to have a couple more iterations. So we start with it. We're going to have 16 marked here. Means we're going to have sort of this path from source to 1 with a weight of a 16. Essentially, this 16 right now is the weight of the path so far, what we have seen so far. Okay, we're not done. And then 2, right? So there's no path from 0 to it, at least initially. We don't see a single edge to it. There's actually a path, we just have not discovered it yet, okay? But that will be done eventually. But right now, from 0 to 2, there's nothing. So we'll put an infinity here. And then for 3, we have 2, right? 0 to 3 is 2. And then for vertex 4, we have a 3, that's the weight, okay? Of the path we have seen so far. That's really what it means right now. And then we have another, we also maintain another array that for the 0, we're starting with a 0. This is the source vertex. That's where we start. This is a given when we execute the algorithm. That's a given. That's an input. Okay. So from 0, let's just say we have found the weight. And 0, I mean 0 to itself is done, right? There's really nothing to it. So we're gonna say this is the weight is found. Now the rest of it, right? We're gonna say false for now. This is initialization. So next, we're gonna examine something. So how do we go about this? So we're going to take a look at this. So from we're gonna look at 1 right now. So now remember, the weight for 0 is done, so we don't look at 0 anymore. So we're gonna go look at the vertices that we have not found the weight yet. So we'll start with a 1, right? The 1, this is a false. We'll start with this. We're gonna check 1. Now with 1, what are the ways? So we're gonna look at this. The way to go to 1 is there are 2 ways to go to 1, right? From 0 to 1, that we already know, that's the initial state. We have a 16, remember, in the previous weight, right? Now there's also another edge that goes to it from 3 to 1. So from 3 to 1, we have a weight of a 12, right? Now we also know the weight, the smallest weight so far for 3, we have a 2. That means that we have a path to 3 from the source 0 to 3. It may be one edge, it may be multiple edges, but so far it's just one edge, right? We're just starting out. So far, the path to 3, the smallest way to get to 3, shortest path to 3, essentially, that's what it means. The shortest path to 3 is 2 so far. So we essentially just add on this additional edge, right? Remember, the weight of the path is to add on the weights of all the edges, right? So we know what's the weight of the whole path up to 3. So now we know if we have an alternative path to 1, that means going through via 3 then to 1. So it's basically add on the previous, which was 2, right? Add 12. Now remember, 2 right here, right now, is because it's just the edge. Actually, we really need to look at what's in the array because this is the shortest path so far. It may not be just on that edge. This is what we remembered. So we're accumulating some, adding things up. So it was 2. So we know getting to 3 is 2 and plus 12 is 14. So that number 14, it's smaller than what we put in this as saying, oh, previously we knew the smallest weight we had was 16, right? Now we have alternative path to that same node, same vertex, that is a smaller number. It means it's a shorter, it's even shorter path. So that would be preferred. So we're gonna update that path, the weight of that path to 1 to 14. Essentially, we have 0, 3, 1. That's a better, shorter path. So now I have 14 here. Okay. Then we're going to look at 2. Now for 2, really there is no other. Okay, so there's 2. Okay, 2. There is actually. Actually, hold on a second. 2. We're not doing this yet. Are we doing the 2 yet? 2. Okay, we're just looking at one thing. Okay, we're actually just looking at one node now, okay? The next slide is gonna be another node. So next slide, we're gonna look at, we're gonna examine the next one, okay? Let's say is iteration. This is the second iteration of this, loop of the algorithm. So we're gonna look at this number 2, actually. No, hold on a second. It's not, doesn't seem right. So for 2, the weight is infinity. Okay, so now the 2 is infinity. We don't have, as far as we know, here's the thing. We have 3. Let's see, 3. We have this 2, and then we're not touching those. We're not touching 4. 3, we don't have alternative way. 4, we do have alternative way. Let's go back to look at the algorithm. So find the vertex that's closest to the vertex for which the shortest path has not been determined. Okay. Closest. Find the vertex V that is closest for which the shortest path has not been determined. Okay. So we want to find the let's see, find the vertex V that is closest to the source. So the vertex closest to the source has not been determined. Okay. So we're actually trying to find that, update that to 16 and then to 14. Okay, I think it comes to this slide now. 14. Okay. All right, it's a little confusing, I understand, but this slide is, okay. 15, 14. All right, so to 1, now we have, 14, that's 14. And this is a 2, this is a 3, this is still infinity. Now we're gonna do this is, okay, I see. To 3, we'll find the shortest path. Okay. What we're missing here is, okay, we're gonna continue on. We'll look at 2, right? So we're gonna look at 2. There was no path to 2 that was basically is the infinity. So this is gonna continue to be infinity. And then looking at number 3, the vertex 3, so it was at 2. Now, do we have something that's even shorter going via, the other nodes? We don't have, okay, we have another way to come in from 4, right? But then to come in from 4, we need to add the previous value 3 with this new edge, 5. 3 plus 5 is 8, okay? So that's bigger than 2, so we don't update. That still remains 2. And we know this is the shortest to 3. So we say this weight is found. Shortest way found, essentially what it means is the shortest way found. Now for 4, okay, if we go 4, now remember we started with a 3, right? That single edge there. Now do we have another path that's shorter? Let's see. We could have potentially come from 3. So 2 plus 7 is 9, or actually 3, we need to look at this 2, it was 2. 2 plus 3, 7 is 9. And that is bigger than 3, okay? And do we have another way to come in? We don't, right? So 3 remains the shortest. So actually we'll mark that as true right here. Now we're also gonna actually update, we're just gonna update node 1 as well, because now that we have found 4, the shortest to 4 is actually just 3, right? And going to node 1, now previously we say was 14 was the shortest so far. Now actually we'll find an even shorter one, because there's another way to go to. Now we still visit this node because it keeps updating, because we say we have not found the shortest way yet. So we keep updating, we keep visiting this one. So alternatively, previously we say we have a current weight is 13. Now we have alternative from 4, because 4 we have already found the weight, the shortest. So we can use that now as a like path to 4 so far. So that's a 3. So 3 plus 10 is 13. Now 13 is actually shorter than what we had before. So we have an improvement. Essentially we'll have shorter path now for 1. So then we say that's 13. 13 is better, it's shorter. So we'll put it in the 13 now. Okay. Now, so 13, is that what we can, is that the way it's done? I mean, there's potentially, we're not done yet. We're going to continue to visit. Now here, we're going to look at 10, well, look at a 1. The one reason is it can be even shortened, because we now previously it was 13, right? So it was 13. That was what say that was the shortest so far via node 4. Now can we do better? Can we do better? So this iteration, we're going to look at say look at a node. Essentially, let's take a look at node 2. The node 2. Now we know we have found a 4. Right? 4 was marked as true. And note for the node 2 is also found. Now 3 was not found, right? 3 was found. Okay, 3 was found. It's also 2. So these things are set. 3, 4. Now what about 2? The node 2 was not found. So let's look at the 2, right? The 2, we're actually going, there's different ways to go to it, from 1 or from 4. Well, we can go from 4, because 4 we already set. The shortest path to 4 is 3. 3 plus this edge to 2 is 7. It's 7. Now 7, that's set, right? 7 is basically there's no change. But we know this is now, we found it. There's because the 4 will have determined the shortest, and so that's maintains to be 7. Now the other way, it's basically this is the shortest. We find the smallest, essentially the shortest path to it. So then 2 for the vertex 2, we also found this. Now once this is found, we're gonna also update. We're gonna check 1 again. The 1, we'll see the weight for shortest path to 2 is a 7, but there's an edge to 1. So 7 plus 2, 7 plus 2 is actually 10. So we'll say, well, that 10 is an improvement over the previous 13. So essentially we're growing, as you see what's happening is we're growing the shortest path for each node, right? So for each node, we have a shortest path. Now, for example, so we're gonna update, now let's say we'll get to this state. Essentially now we are done, okay? We're into this is the final state. So we have found the shortest path to 3 is 2. So 0, 3, this is the path. The shortest path to this 4 is basically from 0 to 4. The shortest path to 1 is actually going from 0, 4, 3, 1. Okay, you see those dotted lines. And then the shortest path to 2, it's going from 0, 4, 2. So that's the shortest path. So essentially, depends on the source and destination vertices. So you can essentially have, like in this case, we define the source of vertices as 0, starting from 0. And we found the shortest path for every other vertex. Depends on where you're going, right? Imagine you're driving, you're from, Los Angeles to Phoenix, right? Let's say, right? Imagine that you assign meaning to those nodes. So essentially, then you have you found the shortest path. This is this bypass Palm Springs. Okay, just as an example in reality. So we're looking at it in a very abstract manner here, but there's a lot of real applications that you can use this for. So the algorithm is really there's two loops here. The outer loop essentially is to find the vertex that's closest to the source, and the path has not been determined. And then we're gonna mark that vertex as smallest way found if we have examined the shortest path to it. That means this is done. There's no more improvement. So as we're seeing here, the way to determine, for example, here, this this one here, this way for the path from 0 to 1, we're not going this way is too much, right? We're going instead actually via 4 and 2. The reason we can finalize that 1 because now we examine this 2 because it does have a way from 2 get to 1. So this is the shortest path to 2. So we know there's no better improvement to 2. This is the best route to 2. So we just add one more edge back to 1. Is this going to be, smaller or bigger than the previous method? Previously, we say, well, we were going from 4, we got 13 to it, but now we have a better way because now 2 has the shortest. We know there's an alternative way to it. So we'll find the shortest, essentially, is you see how this works. So kind of my explanation can be a little confusing, but we're going to look at the source code a little bit also after this, all right? So this is the shortest path algorithm. It's also called the Dijkstra's algorithm, named after the person that designed it. Okay, another problem that's fundamental to graph. It's also very common. It's called a minimal spanning tree. Now, minimal spanning tree, what is it, right? So now, obviously, the name there's a tree in it, and then we're familiar with the trees, right? So, a practical example here, as you see here, imagine an airline wants to be able to fly from one city to another, but want to cut down a maximum number of connections, like going, find the sort of the shortest way to get to every city. Let's say it's the airline covers all these hubs or different airports. It wants to lower the cost, so so it wants to reduce the connection as much as it can, like remove certain edges, so that it will still be able to reach. You'll still be able to reach all the destinations, but with the smallest number of connections, essentially. So that's really kind of a practical a concept what a minimum spanning tree might be. Now for this particular example, see the edges are weighted. This is actually not directed; it's a undirected graph. Now possible solutions, right? So this just shows. Here's a couple of potential trees. Now the reason it's called spanning means the spanning really means to cover every vertex. Make sure that every vertex is connected, right? That's what it really spanning means. Is like don't leave anything out. So you want to make sure everything is still connected, but find such a minimal tree. Okay. So let's look at a little more, more formal what this really means. So what is a tree? A tree is a simple graph such that if U and V are two vertices, then there's a unique path from U to V. So you don't want to have redundant path, like from between any two vertices, like say between 3 and 5, there's a unique path to it. 3 to 0 to 2 to 5, you see? So that's a tree, essentially. Now, what's a rooted tree? A rooted tree is a tree in which a particular vertex is designated as a root. Now, these are all tree structures. You may say here, I'm going to say the 0 is the root. Here, maybe I have a 3 as the root, and then you just arrange this in a tree, hierarchical structure, if you will. So these are all trees, essentially, if you look at that. All right, so that's a rooted tree. Now, what's a weighted tree? A weighted tree is, there's a weight assigned to all the edges. We have not seen, as previously when we studied trees, we've never really assigned weights to the edges, right? We may have studied a trie, in a trie tree, right? In a trie, we have the edges, they have a meaning, essentially, alphabets, right? That for traversal. But that's not really a weight per se. We're not calculating maximal or minimal or something, right? But anyway, so here we're interested in the weights. So the weight of the tree is the sum of the weights of all the edges. So essentially, if I add up all the numbers on the edges, so that becomes the weight of the tree. And then really the problem here, we want to find such a tree with the smallest weight. That's really, again, you see, we're interested in minimum, maximum values when it comes to the graphs or many other problems. So a spanning tree is essentially all the vertices are in that tree, right? So as I was saying, they need to be all connected in that tree. And then so that picture we saw, that's all examples of a spanning tree. Now we don't know if any of them is the minimal, right, for this particular graph. So that is subject to algorithm to find. So we're going to look at a way to do this. So there are two well-known algorithms, but we're going to focus on one of them, Kruskal's algorithm, and there's a Prim's algorithm. So the Prim's algorithm is what we're going to focus on. Now, instead of reading these, then we're going to just look at an example. What's a Prim's method? So this is our graph. We want to find a minimal spanning tree, meaning we want to find a tree that has all the vertices, and then the weight of the tree is the smallest. Okay. This is kind of hard to read. Can I make this bigger? Let's see. I don't know if I can make this bigger. Let's see. Okay, I'm gonna just make this bigger like this. Okay, so we started with that graph, and what we do here, we'll maintain a couple of things. We maintain a array of vertices. We're starting with the source vertex. Let's say our 0 is the source. And then we also maintain another array or a set. It's the edges of the tree, right? This is the vertices of the tree and the edges of the tree, starting with empty. We have not found any edges, but we start with a single vertex unit. We started with a 0. Now, you could potentially start with anything, right? This is not really a directed tree. Directed graph is undirected. So, I mean, you can pick anything. Let's say we'll start with a 0, okay? So this is how we may go about doing this. And then we'll also maintain, now this is not necessarily we'll maintain. In terms of the algorithm, we don't really maintain that because the accompaniment of the vertices of the tree that eventually we're gonna find the complement here right now, we're starting with the 1, 2, 3, 4, 5, 6, all of them, except the 0. The complement of that set is called n, right? This means these are the remaining vertices we have not included in the tree yet. Okay, just for explanation purposes of the algorithm. So we'll start by examining, starting from the vertex 0. This is what we have in the tree now, is starting with this one thing. We have no edges, so we're going to explore. In fact, we're going to explore sort of a like a breadth first manner. So we explore, there's an edge to 1. So 0 to 1 has a weight of 6. We're going to write this out here so we can, make a clear illustration. From 0 to 2, this edge, the weight is 5. And 0 to 3 have a weight of 2. Okay. Now, among all of these 3, we'll find the smallest. Now remember, we want to find a final tree here with the smallest weight. So it kind of makes sense we'll get the smallest number here. So we'll pick the smallest edge with the smallest weight. And then we'll say we're going to take 3 into our tree, the vertex set. So we're going to include 0 and 3 now, because this has the smallest weight from 0. So we have 3 here. Not only this, we're going to add an edge into it. We found an edge 0 to 3, right? It represented with a parenthesis here, a pair. Now the remaining set of vertices are 1, 2, 4, 5, 6. This is a typo, should not be a 3 here, okay? So now we're going to look at this. We're going to still look at the vertices of the tree. So 0, okay, we can go from 0 to 1. We explore 0 to 1 is still 6, like before. 0 to 2 is 5. Now we don't explore 0 to 3 because, both of them is already in the tree we have found so far. So that's already included here. So we exclude that exploration from 0 to 3, okay? Now we also want to look at 3, right? Remember, this is another vertex. Want to explore 3. Explore 3, we'll look at, okay, 4 is connected to it. Okay, 4 is not in the set of V, so it's okay. We look at this one, 3, 4, which is a weight of 8. So among all of these edges, you see what we're doing? We're growing this tree. We're growing, right? Layer by layer, essentially. That's really conceptually what it means. So we find this smallest number is 5. So now we see that 0, 2 should be included. Okay, so because it's smallest, so we're going to include that vertex 2 into our vertex set for the tree. So now we have 0, 2, 3 now in the vertexes. And then we'll also add this 0, 2 edge into the tree. Okay, so we have grown. Look at the dotted lines. The tree we found so far is, comprises of a 0, 2, 3 vertices with its 2 edges, right? And then so the remaining vertices are 1, 4, 5, 6, right? These are the things we have not put into our tree yet. This is what we have so far. So again, same process. We're going to look at all these vertices in this tree so far and see if there's other edges we should add to it. So 0, 1, it's 6. And we're going to also, now from 0, with 3 and 2, they're already in our edges, so we don't really do them anymore. So we need to look at the outside. Now, from 2, we can go to 5 and 6. So we'll lay them out here. And from 3, we can go to 4. 3, 4 has a weight of 8. So we'll compare all of these weights. So can we grow one more edge, put one more edge into the tree that has a minimum weight? So 2, 6, the edge 2, 6 has a minimum weight of 5. So we're going to add this vertex 6 into our tree. See, this becomes a dotted line now. So we have grown this tree with one more edge right here. Okay, so I hope this is clear by now. So I'm not going to go through all of this. You can, do this by yourself, and hope this is clear. So this is how you do it, one by one. Each time you grow by another edge with the minimal weight out of the tree from any possible node out of the tree, any possible vertices, essentially. All right, so that is that. I'm gonna go back to that view. Okay, so just a summary. So we have looked at a tree, a couple of concepts. A tree is essentially a pair of two sets, a set of vertices and a set of edges. That's how we kind of just mathematically represent a graph. In an undirected graph, the edges are not directional. In that, so the elements of E, essentially the edges, are unordered pairs, right? So not directional. And then in a directed graph, the edges are ordered pairs. So there's direction from U to V. And then we'll also look at some concepts as, for example, a subgraph. So this minimal spanning tree, that's a subgraph, right? So that's actually a subgraph. So H is a subgraph of G if every vertex is a vertex of H is a vertex of a G. So all the vertices of G need to be still in your subgraph. And then also every edge is an edge of G. So essentially, it's like a subset, right? Edges and vertices, they're all, just a part of a original graph. So there's a subgraph, like a minimum spanning tree. Now, two vertices in an undirected graph are adjacent if there's an edge between them, right? This is the concept of adjacency. Adjacency list, adjacency matrix representation of a graph. A loop is essentially is a loop on a single vertex, right? A simple graph is there's no loops and there's no parallel edges. Parallel edges go in the same direction, or if you have no direction, you have two edges from between the same pair of vertices. Those are parallel edges. So we are not really studying those two features of graphs. So we're studying simple graphs here. Simple path. Simple path means you may have a circle, but essentially all the inner vertices are distinct. The first and the last could be the same. That means you have a completing a circle, right? A cycle, essentially. So a cycle really means a simple path in which the first and last are the same. So you have a cycle, not a loop. A loop is a loop. So an undirected graph is connected if there's a path between any vertices, any pairs of vertices. There's a path, from one vertex to another, any one of them. That means this whole graph is connected. So we'll look at the two sort of important algorithms of graphs. One is the shortest path. There's different ways to do it, but Dijkstra's algorithm is what we're discussing here. And so what it does is it finds the shortest distance from one vertex to another. And then, weighted graph, we know what the weighted graph is. Essentially, the edges have weights. It could be zero, but it's not negative weight. Now, there could be potential graphs with the negative weights, but it's a little more complex. That's not what we're studying here. So we're studying non-negative weights. A tree in which a particular vertex is designated as a root is called a rooted tree. When we study graphs, the subgraphs that are trees, normally we don't really care so much about roots. But if it would designate a root, and then we'll call it a rooted tree. Okay. Now a tree T is called a spanning tree. So essentially, it has to contain all the vertices of the original graph G. You cannot leave any single one out. That would be a spanning tree. If you leave a vertex out, you have only a portion of vertices, then it's a subgraph, not necessarily a spanning tree, right? That's really what a spanning tree here is. So that's really that about the lecture here. And let's see, take a look some code here. So it's in chapter 20 in the goodie bag. And as you see, we have 3 folders here. So first is the basic graph type. And this graph type has the graph traversal algorithm implemented here. So there's two types of traversal, as we explained: a depth first traversal, or maybe as a breadth first traversal. So there's two primary traversal that's in here. So implementations here, you can explore this code. So I'm not going to look in this code. The code is actually not that complicated in terms of traversal. It's fairly straightforward. And go ahead and take a look. Okay. And then that's the basic graph data structure. And then in terms of the shortest path, the primary algorithm here that we're talking about, the Dijkstra's algorithm, is implemented in here. Now, this, so let me actually kind of go through this a little bit, because that's really what we're explaining. It was a little, seems like a little confusing, but hopefully is maybe a little more clear in terms of this code. So the step one, actually, let's go back to this. Where's the, let's see. Okay. Let's see if I can find the algorithm outline. So the outline here is the first step is initialize the array smallest weight in this manner. So remember, when we initialize them, we're going from the source vertex. Source vertex is called a vertex. In our example here is 0. That's the index of the array, by the way. And so we're going to initialize it based on the weights. Remember the weights, this is the additional matrix. We store the weights of the edges, right? So from the source to the destination J, we iterated through, let's say we have, you know, 5 vertices here. So this G size, the graph size would be 5. And so we initialize the smallest weights from 0 to 4 indexes as the weights. That's really exactly what we're doing here, right? Now remember, in this weights matrix, if there's no direct edge between two vertices, if there's no path, there's no edge between them, and it would be represented as a infinity, or the maximum double in this case. If we're representing them as a double value, that would be maximum double, okay, as the infinity. Now the step 2 is to set the smallest weight for the source vertex as 0. So we're initializing that smallest weight for the source vertex as 0. And also the weight found, the Boolean array is also true. So we initialize that Boolean array as what this is. We initialize a Boolean array, everything to false, except the source vertex, okay? And then we have a for loop here. So this 3, 4, 5 is in a for loop. And we're looping through m vertices. So step 3 is really here. We're finding a minimal weight. Basically for, see, we're having another loop here. And what we're doing is for every vertex, we're looping through, we're trying to find a minimal weight only for the weights have not been found yet. If the weight for this vertex J has not been found, means the matrix, the array here is a false. And if the smallest weight, what we have so far, the shortest path to that J so far is less than the minimal weight that we have. We're trying to look through which one is the smallest. If this for J is even smaller, and of course this is really trying to find the minimum, as you see, right? And I'm going to say assign that smallest weight, the shortest path to V, to this. Well, actually, the shortest path to V, or V is J, by the way. You see that? we're also going to remember which node it is, which vertex it is. So for that J, and setting that as a minimal weight. So looking for the minimal weight among what we have so far that has not been found, the weights have not been found, or actually smallest weights have not been found, I should say. Find the smallest among them, or find a node, a vertex, and that is identified as the V, and we set that to true. Okay, so in this case, what we're doing here, as actually from this to this slide, is that we'll realize that number 3 is the shortest among all of those that have not been, the weights have not been found. It means 1, 2, 3, 4 among these 4 of them. Obviously, 2 is the smallest. So that's why we set this to true. This is really what this means, right? This is step number 4. And now step number 5 is we're going to update the smallest weights for all the other nodes. So for the weights that are not found yet, like 1, 3, and 4, no, 1, 2, and 4, we need to update them. How do we update them? Right, so we need to see, in this case, the 1, we have found even a shorter path because 3 is found, right? So this 2 plus 12 is 14. That's smaller than what we had initially, 16. So that's why we'll update it. And then for 2, do we have any smaller path to it? Like what we know so far? What we know so far, really, if the weight is not found, the smallest weight, so we have the minimum weight. Remember, the minimum weight is 2. Minimum weight is 2 plus the weight if we have an edge to it. So in the case, actually, where's my, I'm losing my, losing my mouse for some reason. Okay, let me go back to it. So for this 2, like 2 plus, actually, so if you look at this one, right, I want you to understand this. The weights from V to J, now remember this V is the node 3 in this case. The 3 is the smallest. So from 3 to 2, we know this is the infinity, so it doesn't really, doesn't really matter. It's not smaller than infinity. It continues to be infinity for node 2. For node 4, then let's look at node 4. Node 4, we have a 3 to 4. It's a 7. 2 plus 7 is 9, right? Now previously we have 3, so it's not smaller. So that's why it remains the same. Okay, so there's no update here. So that's really what the if statement is. Can we, basically it's saying, can we improve that shortest path to this node J, the vertex J, if via the shortest path we have found so far, V, if it can be improved, then we improve it. So anyway, this is step number 5. So this goes on for n times, right? N is the number of the vertices in the graph. So that's really what this algorithm is. It seems a little complicated, but I hope maybe you should go through this exercise a little bit more by yourself. And the book has actually a more detailed explanation. You're welcome to read the book page by page. It does have more, it has paragraphs to explain this. Hopefully, I'm not confusing you too much, and you, should make sure you digest and understand this algorithm. Okay. All right, so that's pretty much it for the lecture, and I'll take some questions. Let me stop the recording.